Greetings and welcome back. For this video, we are going to be discussing equalizers, or EQs for short. Now, equalizers are the most common form of signal processing that we use in the studio. Engineers and music producers use it on just about every track that goes by, and it's very important in being able to shape the tonal qualities or the timbre of any kind of a recorded or a live sound, or the sound that's coming from a virtual instrument or a hardware synthesizer. Very few tracks get by a mix without being touched by EQ of some kind. So we use it to shape the frequency content of the sound. And we use EQs to enhance the desirable things about a sound, the things that we like perhaps the pluck of a guitar string, or maybe the meat of a snare drum, or the sibilance of a vocal. Or we use it to minimize problems or remove the things that we don't want to hear, which could be the ringing part of a snare drum. Or maybe there's a bass sound that's got too much bass in it, we need to roll a little bit of that out. So EQs are very handy tools that allow us to let all of the instruments that are sitting in a mix have a place to live and blend together better. If you have too many instruments that share similar frequency ranges, they tend to get in each other's way and crowd each other in the mix, and some of them will end up masking others. So we use equalizers to help all of these instruments blend together and create a better, cleaner, cohesive mix. Most engineers that have had some experience will recommend that you use equalizers in a subtractive way. In other words, you use EQs to get rid of the stuff that you don't want in a sound in order to enhance the parts that are already there. One of the things that I see people that are just getting started in this is they use EQs to boost up all of the stuff that they want to hear. So they add a lot of bass to the kick drum, or maybe they put a lot of high mids in the vocals. If you do this too much, first of all, it makes the tracks louder, so your mix gets hotter and hotter as you do that, and it also creates that thing I just described called masking, where if you had, say for instance, a synth bass and a kick drum, both panned in the center of the mix, and you added lots of bass to both of them, they're going to compete unless those bass frequencies are separate enough from each other that they're not going to interact. But that's probably not the case, especially in low frequencies. Now, once the whole mix is done and all of the individual tracks have had maybe a little bit or a lot of EQ placed on them, we also use EQ at the final stage after everything's been mixed when we are mastering, and we do this to give an overall balance to the whole mix. Now, this isn't where we go in and work individually on instruments. We do that when we're mixing. During mastering, we use EQs to get consistency from song to song and make sure that one song doesn't sound overly bright while another song sounds excessively bassy. We also use EQs as a creative musical tool. You can shape the sound in ways that make it very interesting to listen to in a mix. You may have heard the song Pumped Up Kicks by Foster the People. Well, the vocalist in the verses sings through a microphone that's been processed heavily heavily through EQ, but also there's delays and reverbs and other things on there, but it's really the EQ that shapes the sound of that vocal and gives it that really narrow band of frequencies and makes it sound like it's coming out of a cheap little speaker or something like that. So creative uses for EQs are also something that we use them for. Now let's talk about the different types of filters that we use when we are constructing the various types of EQs that we use in our arsenal. So the first kind of filter we'll discuss is the peaking filter. Then we have shelving filters, and we also have high-pass filters, and another filter that you're already familiar with because they are used in synthesizers quite a bit. Analog subtractive synthesizers generally use low-pass filters. So you've already seen that. So how does a peaking filter work? Well, a peaking filter does a boost or a cut around a specific selected center frequency. So when we say boost, that means we are going to be turning up the frequencies that are in a sound that live around whatever your selected center frequency is. So let's say the center frequency is 1 kilohertz or 1000 hertz. So we can either turn that frequency range up, that's called boosting, or if we turn it down, that's called cutting. Now you see in this diagram that there's also some frequencies above and below, so this would be above and below the center frequency that get boosted or cut along with it. That's because it's impossible to create a filter, either analog or digital, that can only enhance or reduce one very specific frequency band. So we have this range of other frequencies above and below a peaking filter that also get boost and cut. So these filters have what's called bandwidth. And the bandwidth determines how wide this range of frequencies above and below the center frequency are going to be. So if we have a wide bandwidth, then there's going to be a lot of included frequencies. And if the bandwidth is very narrow, so it would just come down kind of like this, then we have a narrow bandwidth. Now we have another name for bandwidth. We call it Q. And bandwidth, as I mentioned, that just is how many of the frequencies included in a peaking filter that are above and below the center frequency that we're going to boost and cut. So the other name, Q, stands for quality factor. These two terms can be used interchangeably. They both mean exactly the same thing. But one tricky thing about Q is that when you say the Q is high, that actually means that your bandwidth is very narrow. So they're kind of opposite of each other in the way they're described. A low Q means that you've got a very wide bandwidth. And we usually measure Qs in octave ranges. This is a musical range. This is a musical way of measuring frequencies, and you'll see this in a second when I show you some of the different types of filters that we work with. Shelving filters, these are a little bit different than peaking because they boost or cut frequencies either above a selected cutoff frequency or below. So in the case of a high shelf filter, that allows us to boost or cut frequencies above the selected cutoff frequency. Now in some situations, on a mixing board for instance, that cutoff frequency may be fixed. You might not be able to change it. It might be sitting at 8 kilohertz or 10 kilohertz, 12 kilohertz. On the other side of the scale, we have our low shelf type of filter, and those boost or cut below a specific frequency. So anything below the cutoff frequency, let's say it was set at 60 hertz, that's going to get brought up. And again, sometimes on a mixing board or an EQ, those cutoff frequencies will be fixed and you can't change them. Okay, now there's the ones that we've already been familiarized with, or at least one of them. We have high pass and low pass filters. Now these are filters that don't boost, they only cut. So a low pass filter does exactly what you would expect it to. It lets the low frequencies pass through and cuts out the high frequencies. A high pass filter cuts out the low frequencies and only allows the high frequencies to pass through. All of the other frequencies are attenuated, and attenuating means to turn them down. So what do they look like? Well, we'll get to that in a second. Slope. Now, this is something that describes how drastically the filter reduces the frequencies that are either above or below your selected cutoff frequency. So now we're going to take a look at a picture of it. So here's a typical low-pass filter. So anything that's below what's called the pass band or the cutoff frequency, we call that the pass band. That's what's passing through. Anything that's above that gets gradually attenuated or turned down. Now notice again that it doesn't cut off in a straight line. It's not what we would call a brick wall. Again, it's very difficult to try and create that kind of filter. But we can vary the amount of slope, and it's usually measured in dBs per octave. So a filter that has a pretty gentle slope would have -6 dB per octave. That means for every octave in frequency, the frequencies are reduced by 6 decibels. We also have -12 dB per octave and -24 dB per octave. These filters are also the same kind of filters you find in analog synthesizers, and they're often referred to as a 2-pole or a 4-pole kind of filter. 2-pole being a -12 dB per octave, and 4-pole being -24, and then a single pole is -6 dB per octave. Here's what a high-pass filter looks like. Same idea. All of the high frequencies pass through, and then below your specific selected cutoff frequency, you're going to start to attenuate the lows. These are used quite a bit. I use them on almost every track because there's usually lots of low frequency content that you don't need in the sound, especially for vocals or cymbals or anything where it's mostly high-end stuff, guitars. So those will reduce the low frequencies and get rid of rumbles and things like that you don't want piling up in your mix. So high-pass filters, very common. In fact, you usually see them on the input stage of most mixers to cut out low frequencies that you might be picking up from, say, a vocal microphone. Okay, now we're going to take those different filter types and we're going to put them into a specific type of equalizer. So these are going to use different they're going to mix and match different types of the filters that we've just talked about. Excuse me, and the kinds we have to choose from are selectable frequency EQs, parametric EQs, graphic EQs, and a notch filter. Let's take a look at a selectable frequency EQ. So generally you have different frequencies that you can choose from. So this particular EQ is divided into 3 bands, which you can move around, and there's also a low pass and a high pass, and that just turns the filter on and off. And let's take a look at the high part. So we can select what frequency we're going to be using as the cutoff frequency for this filter. Or I believe in this case it's actually a center frequency because these bands are all parametric or peaking type filters. So we go from 5 hertz, 7 hertz, 10 hertz, 12 point, and these are kilohertz, 12.5 kilohertz, or 15 kilohertz. So this is all up in the upper frequency ranges of what we can hear. The middle band goes from 0.4 or 400 hertz, 800 hertz, 1.5K, 3K, or 5K. The low band goes all the way down to 50 hertz, then 100, 200, 300, and 400 hertz. So there's actually 2 knobs on each one of these. One of them allows us to choose the frequency, center frequency point, and the other one allows us to boost. See the plus sign? That means boost, or the minus sign means cut. Now the bandwidth on a selectable frequency EQ is generally fixed. You can't change that, but you can choose your center frequency point, and you can also boost or cut in either direction around the frequency. Okay, let's take a look at a parametric EQ. Now this one uses similar types of peaking filters. However, the big difference is that we have control over the bandwidth now. So we still have variable overlapping frequency bands. So we're showing 2 bands of this EQ right here. And here's our frequency range. You can see it starts at 30 hertz and goes up to 700. Or we can flip this switch and then everything gets multiplied by 10. So this would be 300 up to 7,000 or 7K. And then this next band up here starts at 100 and goes up to 3K. And again, you can multiply those frequencies by 10 if you want to. So we've got a bit of range of overlap here from 100 up to 700. That's also included in this one here. This center knob shows us our bandwidth or our Q. So over here, the bandwidth is very narrow, so the Q is high. We can turn it up and get our bandwidth nice and wide. So we're going to be taking a wide range of frequencies above or below this selected frequency here. And our Q would be considered to be low here. And then the final knob up on the top determines our boost or our cut. So that's variable as well. Graphic EQs, you don't see these too much in music production. They are typically used more often in a live sound situation where you would be using these to tune the speakers that are in a room. Maybe you have resonant frequencies in the room that you need to dial out, or these could be used for monitors on stage in order to keep them from feeding back or from being excessively rumbly by pulling out the low end. And these are all different center frequencies, and the bandwidth on these filters is pretty narrow. And they're spaced, like I said, according to musical intervals. So if you look here, we've got 1K, and over here is 2K, so that's exactly 1 octave higher because the frequency is twice. And then again, it shows up here twice again at 4K, and then again at 8K, and then another one at 16. So from here to here is 1 octave, and then we divide that octave into 3 equal ranges. So this is a third octave EQ, 31 band EQ, and is very common in live sound situations. But you're not going to see a plugin very often that looks like this. You might see one on a digital mixer though. Now those EQs use sort of a variation of what's called a notch filter. And notch filters, we use those to really hone in on a frequency that we don't want to hear, like the ring of a snare drum, for instance, that will be at a very specific note. And a notch filter has a really narrow bandwidth. You can see it's just slicing out a little piece of our frequency range. It doesn't affect the other sounds that are around it too much. So these are problem solvers for us. We use these to get rid of a very specific range of frequencies and try and leave the other frequencies around it as unaffected as possible. Now let's talk about the different ranges of frequency. How do we apply the EQ? So I've broken it down into 4 frequency ranges and given you the range of frequencies for each one and an idea of what kind of sounds you're going to find in there. So first of all, let's talk about the lows. Now our hearing starts at 20 hertz. So that's where this scale starts at 20 hertz, goes up to about 200. And this is where the main part of your low frequency content, which is going to be your basses, kick drums, and synth basses, they're going to be down here in the lower register of this range here. So if you want to get more boom out of your kick drum or more bottom in your synth bass, that's the frequency range you want to start turning up. Or if you've got too much bass in a signal, that's the range you want to start cutting. There's also a lot of what we engineers refer to as mud or muddiness in this frequency range, and that lives around the 120 to 200 hertz, maybe goes a little bit higher than that, maybe up to 250, 300. If your mix is sounding really muddy, go to your tracks and find out which ones might have a lot of frequency content living in this frequency range and start doing some cutting in there, and it'll clean up your mix surprisingly quite a bit. Above the lows, then we've got our low mids. This goes from about 200 to 1000 hertz or 1K. And this is where the fundamental frequencies of a lot of instrument sounds live. So the loudest frequency in a sound, its fundamental, is generally going to be sitting in this range. And that means that you can make quite a big difference on a sound that is passing through a low-mid filter by making just a small change. By boosting it a little bit or cutting it a little bit, you really will hear quite a big difference because that's where most of the frequency content of most of your sounds are going to exist. Above that, we have our high mids, and this starts at about 1K and goes up to about 8,000 or 8K. Now keep in mind there's a little bit of overlap between these, but these are pretty close to about where these different frequency ranges start. Now this range here in the high mids, this is where most of what we can hear as humans, and especially where the center frequencies of the human voice are located. So this is where you go if you're looking to increase clarity, brightness, and intelligibility in a track. This could be a guitar pluck, it could be the beater of a kick drum, it could be the quality of a person's voice. All of that stuff lives in the 1,000 to 8,000 hertz range, and that's where you go if you want to try and make a track sound a little bit more upfront and clear in a mix. Above that, we've got our high frequency range. This goes from about 8,000 up to 20,000, which is the top end of human hearing if you have perfect hearing. As you get older, this number goes down, and coincidentally, women tend to hear better in this frequency range, the high mids and the highs, than men do. And interestingly enough, that is partly due to our evolution, and babies crying have a lot of frequency content right in here. So if you've got a female in the room and they're saying that a track sounds excessively bright or has a lot of high mids in it, you should listen, because a lot of times they are correct and they may be hearing things that you can't. And up in this range of the very highs, this is where all of the overtones and the harmonics of most of your instruments are, especially things like cymbals and any kind of metallic sounds. So if you want to add more of that kind of shimmer or sparkle, or some engineers call it air, that's where you reach and turn up that knob there. So those are our 4 primary bands of frequency: lows, low mids, high mids, and highs. I hope you enjoyed this video, and we will catch you next time. Thank you.